In this video, we're going to investigate when a geometric series is convergent. And a geometric series is just the sum of a geometric sequence. So we take all the terms of a geometric sequence that we learned about in the last section of notes, and we add those terms together. So, by our definition, the kth partial sum, so we're even told that our first step should be to try to find the kth partial sum, and then investigate when that kth partial sum will have a limit that makes sense. So our first job is then to write down the kth partial sum. Remember, sk is the sum, as n goes from 0 to k, so for some finite k, of the terms of our series. So in terms of our geometric series, this is going to be a0 plus a0 times r plus a0 times r squared, all the way up to a0 times k, or to the times r to the power k. So this is a formula for sk. If we multiply this formula for sk by r, then r times sk is equal to a naught times r, just shifts the power by 1. So a naught times r plus a naught times r squared plus all the way up to a naught times r to the power k. But then there's one more. There's a naught times r to the power k plus 1. And at this point, we're trying to find a formula for sk, so now we notice there's a lot of repeats in these two formulas, and so we can subtract these two. On the left-hand side here, we have the formula for the partial sum, or the symbol for the partial sum, s sub k, minus r times s sub k. But on the right-hand side, a whole bunch of stuff cancels. We see that all these terms are in common for both, and when we subtract, those are going to be gone. Okay, they're going to cancel out. We're left with the first term, a sub 0, and then we're subtracting off the second line. So then the last term here is minus a sub 0 times r to the power k plus 1. Okay? And our job is to solve this for s sub k, so we can factor out s sub k on this side. And here we have 1 minus r left over. And on this side we can factor out our a0, and we're left with r to the power k plus 1, 1 minus r to the power k plus 1. And after some work here, we can just divide through by 1 minus r, as long as r is not 1. So here's our first criteria. If r is not 1, then we can divide through, and our partial sum here becomes a0 times 1 minus r to the k plus 1 divided by 1 minus r. And so this is a formula for the kth partial sum of a geometric series. What we'd like to do now is try to find out when is this thing going to be convergent. So let's go to a new page here, and we can write down our formula for the partial sum s sub k is equal to a naught 1 minus r to the power k plus 1 over 1 minus r. And remember, the r and the a naught are both given in the equation of the geometric series, so those are known numbers, and the limit here, so if we're going to try to find out if this thing converges, we have to take the limit as k approaches infinity of this formula for s sub k. We take the limit as the partial sums go out the series, so we add up as more and more and more and more and more and more and more terms, so until we get all of the terms. And so this is going to be the limit, of course, k approaches infinity, a naught times 1 minus r to the power k plus 1 over 1 minus r. And then the limit is only going to care about this one term that has a power of k in it. Everything else is not going to be involved here. And so our answer is going to be a naught times 1 minus, and here's our limit. Limit as k approaches infinity, r to the k plus 1. All divided by 1 minus r. And this limit right here is going to now give us the criteria for when this series converges and when it doesn't. So the limit as k approaches infinity, r to the power k plus 1. What's going to happen with this limit? Well, if r is bigger than 1, so if r is greater than 1, then taking powers of r and making them bigger powers of r is going to make this thing blow up. So this will be plus infinity if the absolute value of r is greater than 1. Okay? I should say it does not exist. So if r is positive and greater than 1, then it's plus infinity. If it's negative and greater than 1, then it's jumping back and forth, but it's not going to exist. So let's just write that as dne if the absolute value of r is greater than 1. On the other hand, if the absolute value of r is less than 1, so if r is a number smaller than 1, then taking bigger and bigger powers of r is just going to make it smaller. Okay, so this limit equals 0 if the absolute value of r is less than 1. So there we go. That's going to give us some convergence there. Now, the other cases are when r equals 1, we already said in the last page that r equals 1 breaks down this point. So r can't be 1 from this point of view, but if we think of what it means for a geometric series to have r equal to 1, then we will see, so I'm going to go off on a short tangent here, but let's look at two cases here. If r equals 1, then our geometric series looks like n, 0 to infinity, a naught, 1 to the n. This is just a naught plus a naught plus a naught, etc. And there's no way that this is going to add up to a finite number unless a naught is 0, in which case, why are you writing this as a series anyway, right? So this thing is going to be divergent. It's going to be a naught times n, or a naught times infinity, definitely divergent. It's just going to add up to an infinite, or maybe minus infinity, depending on the sign of a naught. If r equals to minus 1, what happens? So now our geometric series is going to look like a naught, negative 1 to the n, and this is going to look like a naught, minus a naught, plus a naught, minus a naught, etc. Plus, minus, is going to keep alternating back and forth. But the problem is that if you take, say, 2 of these, add them up, you get 0, right? Add up the next one, you get a naught, etc. And so this is going to have, if we try to write down the partial sums, S0 is a naught, S1 is 0, S2 is a0 or a naught, S3 is 0, S4 is a naught, S5 is 0, etc., right? And so the idea here is that the partial sum is just going to keep going back and forth between 0 and a naught, and that's also going to be divergent. That's never going to converge. It's going to be impossible. It just keeps going back and forth between a naught and 0, a naught and 0. Okay, so at this point we've excluded r equal 1 and r equal negative 1. Those are not allowed as our common ratios. And now we go back over here, and based on this conversation, we can now exclude all ratios that have a magnitude bigger than 1, absolute value bigger than 1. And what we're left with is just ratios that have a magnitude of less than 1. And even if r is negative here, the limit here is still going to be 0. Okay, and what we end up with is that if the magnitude of our ratio is less than 1, then our series converges. So I'll write out the whole series. N equals 0 to infinity, a naught, r to the n. This is going to be convergent. Let me write it out in words. So this is convergent. And its sum is this limit. So in this limit, the power r to the k plus 1, that power goes to 0 as k goes to infinity. And what we're left with is the following. This sum, n from 0 to infinity, a naught, r to the n, is just going to leave us with a naught over 1 minus r. And so this is the sum of a geometric series provided our common ratio, r, has a magnitude less than 1. Okay? And if our common ratio is anything other than this, so if its magnitude is equal to 1 or larger than 1, then our geometric series diverges. The partial sum still makes sense in most cases, except for when r equals 1. The partial sum still makes sense, but the total sum does not make any sense. Okay? So the series diverges otherwise.